My name is Matt Gurdon.
I'm Charlie Alexander.
I'm Andre Andriola.
And this is Design Phase 1 for Team 12. In this presentation, we're going to cover project planning, project management, the identification of customer needs, the target specifications that we're going to set based off these needs, and the economics of our project. So originally, we were discussing concepts that we could base our BRG on, and we came to the conclusion that we are going to focus on 11th grade high school physics. The concepts that we'll cover are in the Virginia SOL standard PH5 and PH6. They include linear motion, potential energy, kinetic energy, linear momentum, angular momentum. The students will predict the path of the ball in the BRG, and they will create a hypothesis and then test it by actually using the BRG. Our key business goals, one is customer focus. The idea is to teach these kids physics. So our customers and teachers, we're going to focus on them so we can get the best product for the best teaching we can possibly make. This will facilitate physics education. We want it to also be able to continue to be used in the classroom and to be affordable and user-friendly. The potential market, customers, our main market is high school teachers. They're the ones who will be implementing the product. We also want to target school boards. They're the ones who will approve it and discuss it. And then we have secondary markets as well, including homeschool teachers, science camps, and college-level introductory physics teachers, which may be providing similar coursework as high school physics.
So for our use case scenario, we have our primary stakeholders are going to be the teachers because they're going to be the ones that physically hold the object in storage and whatnot, and they'll use it year after year. Whereas for the secondary stakeholders, they'll be the students because when they take the specific physics course that the BRG will be designed for, they will use it as it's meant to learn more about the physics concepts that they're establishing in lectures. So the basic flow, the teachers want to implement concepts learned in class. So they will assemble the product, and then the students will use the knowledge that they've learned in their physics class to hopefully apply it using basic calculations to create a hypothesis on how fast the ball enter and exit as the ping pong ball traverses the BRG. And then they'll test the hypothesis to see how accurate it is, and then it will be repackaged. Then for the alternative flow, we're also using the potential for the Arduino to be programmed in order to track the progression or the movement of the ping pong ball. And for our competitive benchmarking, we looked at some competitive products. One of them is from the company Flynn Scientific. This is from their website. It's the Connect STEM Explorations roller coaster building set. So it's based on a lot of the same principles of kinetic energy and motion that we're using in our BRG. As a result, we created some important metrics and we compared them to the charts. So one of our important metrics is the speed of the projectile, which we've established in both the BRG and the Connect kit. The size of the projectile, the length of the course, boundary dimensions, and then the total mass. So these are all things that we need to consider when we make our product, because we need it to be easy to assemble, easy to put, easy to package and repackage, and then we also need to make it as cheap as possible.
So next we have a Gantt chart, which is used to demonstrate our project planning. And we begin with customer needs, which is followed by target specs, and then intellectual properties, which is all under phase 1. And then we start phase 2, which is concept generation, concept tasking, and then we begin on phase 3, which is product designing, industrial design, design manufacturing, and analyzing the economics. And then we'll end with phase 4, which is where we can start prototyping, and then we'll have our final presentation. So under project management, the whole project is expected to last approximately 12 weeks. So we have our product designing, manufacturing design, and industrial design can be done simultaneously, which helps us save time. And then we have 4 phases, which I just talked about. And then once we finish phase 3, we can start prototyping and the presentation. And then next we have our customer interviews. And we separated it into likes and dislikes. And under dislikes, you can see that from our interviews, we found that people thought it could be too complex to be used for beginning physics, and then it can be too much work or effort for how much time you need in the classroom, and then the design can be tedious for students and teachers as well, and then it can also be expensive just being an accessory to the classroom, and that's definitely a big factor when school boards are trying to make a budget. And then it wasn't interactive enough with the user, so we'll have to definitely include ways for the customer to implement ways that the user inputs things with the Arduino. And then finally, it can be difficult to set up. And then with the likes, we have, it's better than teaching from the book. Like the book, a lot of kids zone out. You're just hearing someone lecture the whole time. But with this course, you're actually able to see the things being done. So that makes it easier for the students to understand the laws of physics. And then we also have the creativity during the design process. So it helps kids interact with each other and it has team building, and it absolutely includes the entire class, which is a nice thing for teachers. And it also helps see all the laws of physics work together. So here are our customer needs, and we'll start with the student. The students found that they need it to be exciting because they're in school all day. They're not going to pay attention unless they're actually interested in what they're doing. And then they want it to be challenging. You don't want it to be too easy to where you're going through the motion and not actually learning the material for the class. And then it needs to engage with the student. They want to be able to design the actual course itself, like implement ways to change the course throughout the way. And then they want relevant topics being taught in the class to be used on the product. And then the teachers need it to be reinforcing the concepts they're teaching. That way it's not just side facts about physics, but they can actually use it to understand what will be tested on. And they need it to be low cost. If they use it with their own money, they definitely don't want to shell out a bunch of money. Or if they want to go to the school board, then they're going to have to show them that it's actually worth the money. And then it has to include the whole class. You don't want 3 students working on this and then the rest of the students doing other work. You need to include the whole class. And then finally, it needs to mentally stimulate the students. That way they're interacting with it and not just talking to each other the entire time.
So lastly, we have our economic projections. At this stage, it's very basic economic projections based off competitive benchmarking data and based off the materials that we know we are going to have. As far as specific manufacturing and other specific materials, they're not taken into consideration yet. We're going to assume the cost, selling price, and demand will remain constant. This is a scenario 1 case. Our expenses that we have calculated are $40 Arduino and servo motor to turn a wheel. $15 is our estimate for manufacturing materials at the moment, and $10,000 annual fixed expenses needs to be covered. This is the graph that we've created with total revenue, total cost, fixed costs, our variable costs, and our profit. We've calculated with all this that our break-even point is 105 units sold, and that is with a selling price of 150. The 150 is a little expensive compared to benchmarking data, like the Kinects was about approximately $40. But with the Arduino, with the product we're selling, we think teachers will buy it. They can continue to use it. It's got an Arduino and programs, a servo motor. It's a little more high tech, and we think the price matches the product. So lastly, we're gonna, in the future, work on more accurate economic forecasting, figure out a little more specifically what we're gonna be cost to make this thing, what we're gonna actually sell it for, maybe change a little things. We're gonna update the project schedule. We're going to cover intellectual property, such as our patents that we're going to go for. We're going to go through concept generation and selection and the failure mode analysis that will accompany that. Any further questions, please feel free to reach out to any one of us in Team 12.